Huh? How are we doing today? Great. Awesome. Look, we're going to finish up this chapter 10 today, and I'll take a little time to sort of go over the test as well, which is on Monday. Remember, there's no class on Friday, and unfortunately, I'll be out most of the day on Friday. I'm going to a conference. And I'll be here in the morning, though, so if you want to come see me early, like at 8 o'clock, then please do that. We'll have a help session tomorrow at 3 o'clock. It'll be in Beauregard 104. And tomorrow's Thursday. Yeah, 3 o'clock in Beauregard 104. I sent an email out about that yesterday or the day before. Chapter 10, I know it seems quick with chapter 10, but it's a pretty short chapter. There are really three big ideas. Temperature scales, linear expansion, and then the ideal gas law. The first and third of those you've already seen in chemistry. You should have anyway. Linear expansion, you've seen these expansion joints in the roads, like you go across the bridges, you hear the whoom, whoom, whoom. That's what these are. What those are for is that when your bridge heats up, is that it gets bigger. And these linear expansion joints, they just provide a way for the bridge to expand and to decrease in size without actually making the structure buckle. And so we see this linear expansion a lot. The way we calculate linear expansion, we have our delta L. That's going to be our change in length. So say I have a material and it has a certain length, L naught. That's its initial length at some temperature, T. And when I heat it up, it increases in length by delta L. And we can calculate that delta L is proportional to our coefficient of linear expansion. That's alpha. You have a table on your data sheet that has alphas for different materials. This is our original length, and then that's our change in temperature. So these are fairly straightforward as far as working the problems. Though we'll look at some conceptual problems in just a bit that you have to think a little bit more about them. These are coefficients of linear expansion. Notice that they're different. So some materials will expand at a greater rate or expand more than other materials. Which of these materials will expand the most? Is it aluminum or concrete? Or aluminum or steel, rather? Aluminum has the highest coefficient of linear expansion. Steel has the smallest. Which one expands the most when it's heated up? The aluminum. Right, the aluminum expands more because my change in length is proportional to my change in length is proportional to my coefficient of linear expansion. And so if the coefficient of linear expansion goes up, then the delta L also goes up. Bigger coefficient of linear expansion means that it expands more. It also means that it expands at a greater rate. It'll expand faster. Let's try a problem. No, let's not do this one. Let's look in the back. I think I have one in the back. One that's more like what you'll see. I hope I have one. There we go. Let's do number 24. That should be exam 4 on number 24. I'm going to give you the coefficient of linear expansion for steel here. Alpha for steel is 11 times 10 to the 6th. To the negative 6, rather. And the units for that are degrees Celsius to the negative 1. Let me work on that one. I'm going to see if I got another one here for you. All right, doing really well. On these, it's really just picking out what the numbers are and knowing how to apply the equation. Let's stop in about 5 or 10 seconds. Stop at 225. 225. Okay, good. B is right. To find delta L, I say delta L is equal to L naught alpha delta T. L naught is this 25 meters. That's its original length. The longer an object is, the longer it's going to expand as the temperature increases. There's just more material there to expand. Alpha is that 11 times 10 to the minus 6. That likely will not be in the problem. You'll have to look on your table to find that coefficient of linear expansion on your equation sheet. And then my change in temperature is going to be 40 degrees. That's my final temperature, minus 0. That was my initial temperature. And when you get this, you get 0.011. That's the change in length, but I'm looking for the final length. And so I add that to 25 to get B, 25.011. It'll be something similar to that like you'll see on the test. Let's look at some other things, some other similar questions that'll be more conceptual. We'll go back up to our notes. The answer to this one, if you want to do this later, is D. But don't sweat it too much. It's kind of, you got to calculate the period. It's not difficult. Y'all could do it. It takes a little more time. Okay, let's see. Oh, wedding picture. So we got this wedding picture when we got married 15 years ago. We were married 15 years in January. But we got this wedding picture that was made out of crystal. Crystal, it was a nice picture. And you see in my house, there are things that I make that my wife can't make because I'm from Mississippi and she's from Missouri, and they just don't know how to make things like this in Missouri, like cornbread, sweet tea, and stuff like that. So she always has me make sweet tea. She just doesn't put enough sugar in it, right? But I was making some sweet tea in our really nice crystal pitcher that we got from somebody for our wedding. And what did I do? I boiled the tea on the stove, and I put the hot tea into and it shattered, or cracked, big old crack in it. And my wife, like, she's very understanding and forgiving and all that. And she just sort of... But anyway, when you put hot liquid into something like that, it expands, right? And depending upon the rate of thermal expansion, for crystal, it's kind of high. It can crack the material. So it causes some kitchenware to crack or break when you put a hot liquid inside of it. And the reason is that the inside of it is expanding, but the outside of it does not expand. So if we think of this dish, right, I get this side of the dish will get bigger because it's at a high temperature. But over here, when I'm at a low temperature, this side stays the same. And so that's what causes these materials to break. Pyrex, on the other hand, has a low rate of thermal expansion, has a much lower coefficient of expansion. Right, y'all use Pyrex in lab and other places. Your kitchen, you have these Pyrex glass dishes. It's glass, it's been heat treated and made such that its rate of thermal expansion is less than what it is for just regular glass. And so if you have a lower rate of thermal expansion, then it won't expand as much here, or very little at all, and that will keep the dish from cracking. So that's what Pyrex is. It's just a special kind of glass. We talked about the thermostat, right? The thermostat where usually it's round and you have a dial on it with an arrow. You can move it like this. And if you ever take it off, you see this coil inside of there. That coil is a bimetallic strip. A bimetallic strip can be steel and brass, for example. It can be any two metals that are just stuck to one another. They're welded to one another. And then if you heat up that strip of metal, because these have different rates of expansion, they'll bend in one direction or the other. So for example, The coefficient for steel, which we saw before, is 11 times 10 to the minus 6. The coefficient for brass is 19 times 10 to the minus 6 degrees Celsius to the -1. So if I have this bimetallic strip with those coefficients of linear expansion, and I heat up this strip, what is it going to do? Is it going to bend up, or is it going to bend down? Now, one of these strips will expand at a greater rate than the other, and it will cause the strip to either bend up or to bend down. So that's the question for you. Does this strip bend either up or down when it's heated? A, up, B, down. Does it bend up? That is, the whole strip will sort of bend in this direction, or will it bend downward like that? All right, let's stop at 40 seconds. Or I'll go to 43. Okay, good. A is right. It's going to bend up, because notice that this value is bigger. The coefficient for brass is bigger than that for steel. So when you heat this thing up, the brass side is going to get long, and the steel side will remain short. But because they're stuck together, instead of just the brass getting longer, what's really going to happen is that this thing will sort of look like this. It'll get into an arc, where now the brass side is longer than the steel side, because it's on the outer lane of the track, right? That's a longer distance here. So it's actually expanded. And that's the same idea behind these thermostats, that you have this bimetallic strip. And when the temperature changes, even just by a degree or whatever, this strip will either coil up or relax and change the temperature on your thermostat, and either cause your heat or your air conditioning to come on. Most of us have not those types of thermostats anymore. You probably don't see those very much at all. All right. Yeah, there's the thermostat. Let's try this quick test, and we'll see one similar to this in the concept test soon. So here I have a steel tape measure, and it's used to give measurements at hot temperatures. So it's designed to work at very high temperatures. What if you have it at just normal temperatures? How does that affect the length measurements? Do the measurements that you measure, are they too large? Are they accurate? Are they too small? Or do you just need more information? Okay, I'm going to help you out, because y'all are sort of split between A and C, and it is either A or C. Let me help you out. It helps with this to draw a picture. This is my ruler at hot temperatures. And then let's say this is the object that I'm measuring. All right, I measure that object to be 3 units long. This is at hot temperatures. Now this is my ruler at regular temperatures, at just room temperature. It gets smaller, right? The ruler gets smaller because it's at lower temperature now. So is this ruler going to measure this object to be 3 units long, more than 3 units long, or less than 3 units long? This ruler measured it to be 3 units long, because it was designed to measure at high temperatures. But what about this ruler? What has happened to the distance, or to the tick marks on the ruler? Is it now going to be measuring it at more than 3, less than 3, more or less than 3? All right, let's stop in just a few seconds. I'll stop at 2:05. Okay, that's good. A is right. It's going to measure them to be longer than it actually is. Let me finish drawing this picture. So my tick marks now will be closer together. And so they squeeze together. So whereas it's measured 3 units long here it's measured like 5 units long. And so the effective measurement is too long. It's longer than the actual object, which is actually 3 units long. Okay? We'll see similar questions when we do the concept test soon. Good job doing that. That wasn't quite 90%, was it? But you've had 3 very close to 90%. So how many tickles does it take to make an octopus laugh? 10. 10 tickles. You get it? Tentacles, like an octopus has tentacles? All right.
8 tentacles. It's got 8 tentacles.
Okay, thank you. Okay, so the last thing we'll see is the ideal gas law. You've seen the ideal gas law? I know you have, but just sort of one last Yahoo. Ideal gas law, this applies to ideal gases which have a low density. Most gases have a low density. Atoms move randomly and exert no forces on one another. They don't touch the gas particles. That's when we say they don't exert forces on one another, they just don't touch. They might interact some, but they don't touch. We often use moles to express the amount of a gas. And then Avogadro's number gives the number of particles, atoms, or molecules in a gas. Right, and Avogadro's number, you don't need to know this, it's on your equation sheet. Many of you might know it. It's 6.02 times 10 to the 23rd. It just occurred to me, I learned that a friend of mine, a student, is getting married on June 2nd. I wonder if it's because of Avogadro's number. One of them's a biology major, it might. Yeah, all right, 10:23 a.m. on June 2nd. That's reasonable for a wedding. All right. This is based on the number of atoms in 12 grams of carbon-12. You don't need to know that, but that's the number of atoms that are in 12 grams of carbon-12. That's where that number comes from. Okay. A mole is a mole is a mole. So any mole of any substance will have this number of molecules, atoms, or particles. So if we had a mole of students, for example, would they fit in this room? I bet we could get them in this room. But no, a mole is that number times whatever you're dealing with. The molar mass, on the other hand, is the mass of the substance. Or excuse me, the molar mass is equal to the mass of 1 mole. And so the number of moles is the mass of the substance. Divided by the molar mass. And so to calculate the mass of an atom, for example, you would say the molar mass of helium Alright, this is the mass. If I have 1 mole of helium, that's what the mass of that would be. And if I want to know the mass of an individual helium atom, then I would divide by what value? Because this is the mass of 1 mole of helium atoms. I would divide this by Avogadro's number. Right. So I divide it by Avogadro's number, Na. So if you just wanted to know the mass of a helium atom, you would take its molar mass, 4 grams per mole, divided by 6.02 times 10 to the 23. That's in atoms per mole. And it would give you the actual mass of helium instead of minus 24. And that's in grams per atom. Okay? Should have seen this before. I'm going to skip this question. But the greater number of atoms, which is it, the nitrogen or oxygen? They're the same, right? So a mole is a mole is a mole. It doesn't matter about the molar mass. You still have the same number of particles in that. However, if I were to talk about the molar mass, oxygen has more mass in a mole than does nitrogen, right? Because it's CNO, right? Oxygen comes after nitrogen. So you might have a question about what is a mole, sort of exploring that idea. You'll have maybe two questions related to ideal gas law. You're not going to have many from chapter 10, maybe 5 or 6 questions total. The ideal gas law, that's the whole PV equals nRT, is a combination of actually 2 laws. First is Charles' law, is that V is proportional to T. If the temperature goes up, the volume goes up. And then also Boyle's law, which says that pressure is the inverse of volume, is proportional to the inverse of volume. That if your volume gets bigger, your pressure goes down. It's like with breathing, right? How do we breathe? You ever thought about how we breathe? We make our chest cavity bigger. And when our chest cavity gets bigger, it makes the pressure decrease, and then all this air from outside goes into our lungs. That's all we're doing. We're making our chest cavity bigger or smaller. Bigger or smaller. And that's a good application of Boyle's law. If I make V bigger, the pressure inside my lungs decreases, right? Your lungs aren't muscles. They're just bags inside your chest. Then that high pressure air goes into your lungs because it's a lower pressure inside. So as the volume increases, the pressure decreases. And so we write our ideal gas law, PV equals nRT, where R is this universal gas constant, 8.314. That's in joules per mole Kelvin. Just a little alert here. When you're using this, make sure you check your units because your temperature has to be in Kelvin here to be in proper SI units. Your pressure has to be in pascals. Goodness, bless you all. And then volume has to be in cubic meters. You do have a question. Yeah. Yeah.
No.
Oh, yes. I'm sorry. I think we're going to move to a different room. Yeah. Because y'all use a different gas constant. Use the K, I think, Boltzmann's constant. Yeah, because you just check your units. And on your equation sheet, it might even be, both might be given. I don't know. But they don't use SI units in chemistry. I don't know why. No, did I do that? They're not stupid. They're like some of the smartest people I know. But, okay? Here, N is the number of moles. Just check your units, okay? As I was saying, there is an ideal gas law question on your test, and in the OpenStax. Although with OpenStax they use Boltzmann's constant instead of the universal gas constant. I'll show you how they're related. But just be careful of your units. I think I even made a note in there just to make sure that you're converting to proper units. Okay? You can express it with Boltzmann's constant, which is, no, that's not in. Yeah, their constant's different. It's just different units. But this is also the ideal gas law. But here, instead of having N be the number of moles, here N is actually the number of particles. Right? And so we express the gas constant a little bit differently. That's it, I think. A couple of questions here. Let's try this one out. There should be cubic meters there. If you finish this one, go on down to the next one. All right, let's just do about 10 or 15 more seconds. Stopping at 2:30. 2:30. Okay, B is right. The way you do this, you have to be careful with your units. Like I said, it's kind of tricky with your units. PV is nRT. My pressure is 1.5 atmospheres. That's going to be 1.5 times 10 to the 5th pascals. Remember, 1 atmosphere equals 10 to the 5th pascals, 100,000 newtons per square meter. The volume is 0.1 cubic meters. Equal to 10, that's 10 moles, times R is 8.314. And then my temperature, I want to know the temperature. But look, I want to know it in degrees centigrade, not Kelvin. So when I calculate this, it's going to come out in Kelvin. And so I get T is equal to 180 Kelvin. But if I want to calculate the centigrade temperature, I say TC is equal to Kelvin minus 273. So it's going to be 180 minus 273, which is that minus 93. So probably a lot of you put A, is that right? Yeah, A was one of the answers. I don't know how D came about. Oh, D, they probably did. You had a couple of issues, and you put D. One, you didn't convert this to pascals, and then you just took this value, which is actually in Kelvin. So the 2 mistakes there. But you have to convert your pressure to pascals, and then convert your temperature to Celsius. You'll have to, on the test Monday, you'll also have to do some unit conversions. So just watch that. I tried to make it clear in the exam. If you're ever uncertain, look at your units, right? I'm looking for Kelvin, I'm looking for cubic meters, for newtons per square meter, for pressure, pascals. Let's try this next one. On these, you'll want to write down your ideal gas law. Identify the things that are constant, and identify the things that are changing, and then you can figure out which has the higher temperature. All right, let's stop at 110. 110. This seems counterintuitive, but the answer is B, that the one with less material has a lower temperature. Look, don't try to memorize these, but just think, well, P and V are constant. I know that P and V are constant, one, because I have two identical cylinders. That tells me the volume is the same for both. They have the same pressure, so both P and V are constant. And then, I know that R is constant too. If container A contains more gas, that means that the temperature must decrease. So container A with less gas or with more gas has a lower temperature. You can think about it this way, that if I have more gas in this container, it's just not going to be able to move around as much, right? And so if it doesn't move around as much, that means it has less thermal energy. So it's actually the one with the lower amount of material that has the higher temperature. So the cylinder with the higher temperature is container B. All right. Not going to be able to finish all the concept tests. Let me point out something to y'all. I don't know if y'all know that this exists, but we will go over a few of the questions. But if you go onto our website on the online participation, you can find solutions for all the concept tests. I mean, you can always just download the PowerPoint and the text sort of describes the answer. But if you click on these, it will... Oh, do I not have a Chapter 10 solution? Ugh. All right, maybe I'll get to one. I'll try to. But I'll also upload the PowerPoints. Let's look, though, at Chapter 10 a little bit. There were a couple things I wanted to look at. Have we done any of these for Chapter 10? All right. Our Celsius and our Kelvin degrees, I don't know if I mentioned this back when we did this, but we did talk about converting between Celsius and Kelvin, and they're just offset by the 273 Kelvin or 273 degrees. And so the Celsius and the Kelvin degree, they're the same size. Doesn't mean that they're the same temperature. It means that if I have a change in temperature for Celsius and a change in temperature for Kelvin, those are going to be measuring the same change in temperature. Okay, so like 1 Kelvin is not equal to 1 Celsius, but a change in temperature of 1 Kelvin is equal to the change in temperature of 1 Celsius. And that works out on our equation, that whole Tc is equal to T Kelvin minus 273. Right, there's not that 9/5 or 5/9 fraction in there because the size of the degrees are the same. Is there a place, and what is it, when the Kelvin and the Celsius scales agree? That is a temperature where that temperature in Kelvin is the same as that temperature in Celsius, because it just turns out that minus 40 Celsius is equal to minus 40 Fahrenheit. Is there a similar temperature for the Kelvin and Celsius scales? All right, let's stop at 45. 45. Okay, good. D is right. There is none because they're separated by 273 degrees. I think we've already talked about this. I'm going to skip over some of these. I want to get to some of the more difficult ones. This is just like the one that we did earlier. Sorry, y'all want to write down the answers? C was that one. D. Let's look at this one. So I have a steel ring. The steel ring's right here. And then I want to heat, and then I have some material, a bar, some material in between. I want to heat up this whole thing so that eventually this bar touches the steel ring. But people do this. They make systems that don't fit together when they're at some temperature, but then they do fit together when they're at different temperature. What material must this be in order for that to happen? Y'all are awesome. Ask your neighbor if you're not sure. Think about their coefficients of linear expansion and how they're different. And what must the material of the rod do? Must it have a bigger or a smaller coefficient of linear expansion in order to touch the ring? If it's bigger, then it's aluminum. If it's smaller, it's going to be glass. Or if it could be the same, then it could just be steel. All right, let's stop at 130. 130. Okay, good. A is right. As you heat this thing up, you want the bar to get longer faster than the ring. And so you want something with a bigger coefficient of linear expansion, and the thing with a bigger coefficient of linear expansion is aluminum. So I'd have this as steel, and this is aluminum, and then eventually, as they get bigger, the aluminum rod will actually touch. Right? Y'all have done this before, or you might have seen people, like if they have two parts that are stuck together and they want to try to get them apart, they can heat them up or cool them down. Let's look at the next question, actually. I think it's related to that. Say you want to take apart a couple of aluminum parts that are held together by steel screws, but the screws are stuck, like they're too tight inside the part. What do? Do you heat it up or you cool it down if you want to get these things apart? Aluminum parts held together by steel screws. Now, you have two things, right? You have a thing with a hole in it, like this. That's like the hole that the screw goes into. And if I heat this thing up, it's going to get bigger. And the hole will get bigger. But I also have the screw. Because as I heat it up, it's going to get bigger too. And so what you want to do is to either heat it up or cool it down such that the screw is going to be smaller than the hole. All right, let's stop at 105. Okay, good. In this case, you would heat it up because I have this steel part with an aluminum screw inside of it, or excuse me, an aluminum part with a steel screw. This is steel. If I heat this up, since the aluminum has a higher coefficient of linear expansion, the hole is going to get bigger faster than the screw does, because the coefficient of linear expansion for aluminum is bigger than that of steel. If it was switched, by the way, like if I had a steel part with an aluminum screw, what would that be? I wouldn't heat it up. I would cool it off. Like I would actually make it cold, and then that would make the aluminum screw shrink faster than the hole would shrink. Okay? You'll probably see a question something similar to that on the test. You will see something similar to that on the test. I'm going to skip this. We had that one as well already. This one, the oxygen weighs more because it has a higher molar mass. So a mole of oxygen does have more mass than a mole of nitrogen. carbon, nitrogen, oxygen on your periodic table. Okay, I think we're going to stop there. I want to have some time. There are a few more about the ideal gas law. I'm going to post this on the website so you can take a look at it. If you have questions about it, please let me know. I think most of them we've seen, some of them that are like it. We can skim through them if you want to write down the answers while you're here. That's A for 10.9. 10.93 is B. .10 is C, and 10.11 is C. All right, but I'll post those on the website under the concept test soon. All right, I wanted to spend a little bit of time just going over what you'll see on the exam. Okay, so our exam is going to cover chapters 8, 9, and 10. Most of it will be chapters 8 and 9. Chapter 8 is probably the biggest beast on the exam because we had a bunch of stuff in it. But chapter 9 had quite a bit of stuff in it too. So in chapter 8, you're going to have to do net torque. That's like those problems where you say you have these forces acting on this object. What is the net torque on that object? So you'll see net torque, equilibrium, that's the sum of the torques equals 0, right? It's sort of like the seesaw problem. If I have one force over here, what force is required over here to keep it balanced? Something like that. We've seen a bunch of problems like that on OpenStax and in class and what have you. Please do look over your OpenStax. Make sure you work through those. I've pulled, I don't know, 5, 6, 7 questions from those. So it'll be useful. They're not the real esoteric questions. They're ones like we've worked in class. So if you can do the problems we've done in class, then you should be okay. But I would go back and look at the OpenStax too. So equilibrium, you're going to do moment of inertia. For both particles and for objects. You know, objects like a sphere, a cylinder, a rod, that sort of thing. Make sure you know that table, how to use it anyway. You'll have the table. Just make sure you know how to use it. Mallory? Right. So for a particle, where you have, say, several particles that are at different radii from the rotation axis. If you look back, we had a sample problem, or a couple sample problems in that chapter on chapter 8. Goodness bless you. Okay. Newton's second law. That's that whole thing, and there might be combined with finding net torque on this. But the whole deal where you say that the sum of the torques, the net torque, is equal to I times alpha. And then further, there might be some simple kinematics equations, so where you might find alpha and then have to find, you know, theta or omega after a certain duration of time. Where you use those kinematics equations. Those are on your equation sheet. They're really from chapter 7, but you might see a simple extrapolation from Newton's second law, where you first have to find alpha and then you have to find omega or theta. So just, you know, look back through that, work through some of the older exams. You'll get some practice with it. Then kinetic energy. Remember we talked about two different types of kinetic energy. The rotational, that's that 1/2 I omega squared. And then we also had translational, which we had seen back in chapter 5. That's that 1/2 mv squared. And so an object that's moving with a translational speed and with a rotational speed has two types of energy. It has both rotational and translational energy. We worked a problem like that, and I think you had one in your OpenStax as well. There were some other things about the work energy theorem as well, that if I do work on an object, it changes my energy. I don't remember if I put anything like that. I don't want to tell you no because I might have. And then angular momentum, that's that P equals, excuse me, not P equals mv. L equals I omega. Angular momentum. More particularly is that the angular momentum is conserved. L initial is equal to L final. And this came up in several cases, like when I had the figure skater, she pulls her arms in, that changes her moment of inertia, which will change her angular speed. Or you have the kid that jumps onto the merry-go-round, that changes the moment of inertia, which will slow down the merry-go-round. So take a look at that, and then also think about, we had some concept questions about how is angular momentum related to the kinetic energy. That if the angular momentum changes in some way, how does that affect the kinetic energy? Remembering that one is dependent linearly with omega, that's L, the momentum, and one is quadratically with omega, that's the kinetic energy. Look back in the concept test and in the workbook and stuff, we had some sample questions about that, so make sure that you're up on those relationships. Okay, chapter 9 is solids and fluids. You need to know the states of matter. I mean, that's like 3rd grade, so it'll be some basic thing about the organization of the molecules, or, what are the states of matter, that sort of thing. Stress and strain. If I apply a stress, that's F over A, that's our stress. If I apply a stress to a material, it causes a strain. Strain is delta L over L, and that's related by the Young's modulus. Okay? We had some calculations. You'll probably have to do a calculation for that. You will have to do a calculation for that. Either calculating what delta L should be, or maybe calculating what the Young's modulus will be, or calculating the stress, or calculating the strain. One of those things. Just be familiar with that equation and how to use it, what the quantities are. So stress and strain, density and pressure. Density and pressure come up a lot, but in this section, like where you have 1 or 2 questions, it's just basic definitions of density or pressure. Density is mass over volume. Pressure is force over area. Okay? Again, look at your open stacks because you'll see some questions that are similar. Don't just memorize them because I'll change the numbers and might even change the wording up a little bit. But take a look at those. I moved one of your open stacks to Friday night. I'm sorry for that, but it just gives you more time with the answers. So the one on fluids is due Friday, and one on temperature scales is due on Saturday. If you have any questions about them, please let me know. I can help you with them if you're having trouble, but please come to me with the work that you've done on them. Okay, so density and pressure. And then Archimedes Principle. You need to be able to calculate the buoyant force. That's the buoyant force is equal to the density of the fluid, volume of the object, times G. Be able to calculate that. Be able to determine the submerged volume of an object. We did that in class, right? Be able to know when an object is floating that the buoyant force is equal to what? It's equal to the weight. When the object is floating, the buoyant force is equal to the weight. So look back, we've seen a number of questions, and there were a number of questions on your open stacks too. So Archimedes Principle. Oh, pressure at a depth. Lots of stuff in this chapter, and it's all sort of loosely related. So that's going to be the challenge for you, is to keeping it all together, but then also separate in your mind. The pressure at a depth, that's that P equal rho GH. That when I'm at a certain depth in a liquid, I experience a pressure. You need to know Pascal's principle. That is that P1 is equal to P2. That's the hydraulic lift thing. You'll have a hydraulic lift where I'll ask you what is the output force or what is the area required for a certain output force. A hydraulic lift. Look back, every test has a hydraulic lift. So you'll see one similar to one of those. Measurements. Manometer, barometer, those sorts of things where you have two pressures that you're comparing, P1 and P or P naught. And remember that P1 is equal to P naught plus or minus rho GH. And the plus or the minus depends on the level of the fluid. We had some questions where you had to tell which of these are the bigger pressure. You'll have one of those for sure. Oh, and then Archimedes Principle. Oh, motion. You have the equation of continuity, A1V1 equals A2V2. And then also Bernoulli's equation, which is really just the conservation of energy. Kinetic energy, 1/2 rho v squared, plus gravitational potential energy, rho GH, plus the work, which is pressure. That's equivalent to work. So this is equal to a constant value. Big deal with Bernoulli's equation is that if V goes up, P goes down. Right, with the little ping pong ball in the cup, or the blood vessel with the blood that goes faster, the pressure drops. Be able to apply both of those, both in calculations, especially for this one, be able to calculate the new velocity, and then also just conceptually, with Bernoulli's particularly. All right, just a couple more minutes. Not much in chapter 10, really. Temperature scales. You'll have to do a couple conversions, either a problem all by itself or embedded within a problem. I think the ideal gas law, I'm pretty sure you had to convert your temperature. The idea of thermal contact and equilibrium. This is in your OpenStax, which is due on Saturday. Different ways to measure temperatures. There's linear expansion, which we just did. Just a calculation, really. Or you will, I think, I'm pretty sure I put one of those where you have these two parts together. Which one do you heat them up or cool it down to take them apart? Or something similar along that vein. I'm pretty sure I put one of those in there. And then moles and ideal gas law. That's about it. The idea of a mole, what it is, and the ideal gas law, P equals nRT. Both conceptual and calculation. Being able to calculate one of those quantities, and then also, like the problems we just did, if I hold some of them constant, which will change. Test is going to be normal, about 28 questions, maybe 27 or 29 questions. It'll be in the auditorium, which you know can be cold, so bring a jacket. I'll let you start out. I'll be around some on Friday, but not much. So if you want to see me on Friday, shoot me an email tomorrow, okay? But otherwise, let's see if there's anything in front. Oh no, that'd be like a whole test. I don't know. Seriously? Okay. Yeah, there were 5 to 8 total, I think. But they're similar to the ones that we've seen on the old test. So, yeah.